Welcome to my Circuits 1 final review, or starter guide for smart people. Quick disclaimer, I'm not a professor, I'm a sophomore on a co-op who took this class for the first time over the summer at S&T alongside 8 more credit hours, and I got a B. So if that bothers you, get out. If you're in a hurry, I made a 60-second version linked here. There will also be chapters linked in the description. So in the wise words of Coach Kent Murphy,
let's break this down from a fundamental standpoint.
First, the physical properties. Electric charge is measured in coulomb, or about the charge of 6.24 times 10 to the 18 electrons. Current, measured in ampere, is coulomb per second, charge per unit time, like a flow rate. We'll get more into that in voltage, but remember that current flows from positive to negative. That's just an accepted convention. Electrical potential is measured in volt, joules per coulomb, or energy per unit charge. When you think of this pressure flow scenario, the pressure is your voltage, the flow is your current, and the friction that's caused by the valve in the middle is your resistance measured in ohm. In the case of no flow, you still have pressure caused by gravity, which you can replace with charge, but infinite static friction, which prevents the flow. You can derive this from V equals IR. Power in watts is joules per second, energy per unit time. If you take the units for voltage and current, you'll see that charge cancels out, and you see joules per second, so power is VI. Let's step out of physics 2 and into circuits. Elements are either components or sources. The only components you'll have to worry about are resistors, capacitors, and inductors. For sources, you have independent voltage and current sources. Current has the arrow, and dependent sources as well. Branches and nodes define relationships between elements. A branch is a single element, and there are nodes where 2 or more of them join. So there are 2 nodes in this circuit, and 4 in this one. Nodes also define series and parallel. Elements in series share 1 node, and elements in parallel share 2 nodes. Since R3 and R4 share 2 nodes, they're in parallel, and we can reimagine the circuit like this if it makes more sense. So here are some elements in series, parallel, and a mix. You can simplify some circuits. Here's one with resistors and a voltage source. We're going to find the Thevenin equivalent. Resistors in series add to their total, and parallel ones follow the formula 1 over RT equals 1 over R1 plus 1 over R2, which I've arguably made more confusing here. Inductors add the same as resistors, and capacitors are the opposite, where capacitors in series follow the formula and they add in parallel. Kirchhoff's voltage law, KVL, says that the sum of all voltages in a loop equals 0. A loop, not a mesh, they're different. When adding them, pay attention to the signs you run into. This is negative 20 and plus 15. This is where your currents matter. If you're finding I, it goes from positive to negative. KCL is the same thing, but with nodes. Currents going in subtract, currents coming out add. Using these, you can derive some useful tools for engineering. The voltage divider. If we want to find V, it's equal to the total voltage across the resistors times the value of the resistor you're measuring divided by the total resistance. You'll see this in operational amplifiers to multiply voltages. The current divider works with parallel resistors when you find the current going through The current divider works with parallel resistors when you're finding the current going through a single resistor. The total current times the total of the other resistors is divided by the real total resistance. If you have multiple sources and it becomes hard to find a voltage, have you thought about killing them? Well, you can, so long as you add them back at the end. Here we have a voltage and a current source. We'll kill the current first. It becomes open, then solve for V2. We'll call it V21 because we still have to kill the voltage. When you do that, it becomes a short. Find V22 and add the answers to get the real value. You can take a voltage in series with a resistor and turn it into a current source in parallel with the same resistor. The only catch being that the current is V over R, and you can do the inverse as well. You have the tools to do Thevenin and Norton equivalents. Thevenin is a voltage in series with a resistor. If you need the Norton of that, just do the source transformation. It's a current in parallel with a resistor. Mesh currents and node voltage equations. Use the tools and find the voltages and currents with relation to each other. Throw them in a matrix, like so. I've never liked this one, so we're going to gently skip it. Signals. A step function looks like this, u of t. It's easier just to show you. 3u of t minus 1 would be a step of 3 that starts at t equals 1. Then the minus 2 starts at t equals 5, leaving you at v of t greater than 5 equals 1. Ramp functions describe slopes. The coefficients add the slopes. So you'll see here I canceled this slope out to 0 after t equals 5 because 2 minus 2 equals 0. RC circuits. RC circuits are not radio controlled, but resistor capacitor. The current across a capacitor is C dV dt, and do the math to find V of t, but I wrote it right here. For first order differential equations, all you really need to know is V of t equals A e to the negative t over tau. A is arbitrary. You'll solve for it given some known voltage, probably the initial condition, because E will just become 1. And tau is your time constant, which in this case is RC, resistance times capacitance, where capacitance is measured in farad. RL circuits are the same, but with inductors, so their V of t is L di dt, and their time constant is L over R. L is inductance measured in Henry. RLC circuits are a pain, so I went through one after this attempted explanation. But first we have some new Greek letter definitions. Omega naught is your undamped natural frequency, zeta is your dampening ratio, and alpha is your dampening coefficient. The values for these change based on how you solve your RLC circuit. This is a second order differential equation for the KCL method, if they share a node. Omega naught is the square root of 1 over LC, zeta is 1 over 2R square root of LC, and alpha is zeta omega naught. There's a bunch of other stuff here that relate to DiffEq, but I just started that class today, so this is what you should put in your TI Inspire for test day. If zeta is greater than 1, you're overdamped, and when you solve for S, you should get 2 distinct negative numbers. If zeta is 1, it's critically damped. If it's less than 1, it's underdamped. This one scared me because it looks like, yep, imaginary numbers in physics equations. I thought the day I saw those would be far in the future, but no, it was 3 weeks ago. And because we use I for current, we use J for the imaginary number. Each one of these has an equation for the natural response. Once again, you may have to solve for A and A2. But guess what? We're not done. The total response is the natural response plus the particular solution. So when you do your derivative and solve it for S, you'll have a solution in some form to be replaced with constants that you'll solve for. Do the derivatives of your new solution, substitute, and solve. The series Greek letters are right here. You can pause it. I'll move on to the RLC problem. But that's all for circuits 1, I think. Here's our circuit and given values. You'll see R, L, and C share a node, so we'll use the KCL method to define the voltages across each element. The capacitor current is C dV dt. The resistor use V equals IR, and the inductor is this fancy integral I don't really care for because we're just going to take the derivative anyway. After taking the derivative, we divide out our 0.25. You'll see we know Vs, so we substitute it. That's the solution you'll worry about for the particular solution. I couldn't tell you why, but take another derivative and divide out dV dt, then replace dV dt with S. Solve for S, use the quadratic formula or whatever you want. You get 2 distinct negative values for S, so it's overdamped, but we'll check and find zeta. Yep, so we have our unfinished natural response equation that will remain unfinished. Find the particular solution, use 20e to the 5t, replace the coefficient with k, find the derivatives, substitute and solve. That's as far as we go, so congratulations, you got a B.